Good afternoon, ladies and gentlemen. Can everyone hear me?
Yes, sir. Yes, sir.
Okay, awesome. So let's give another minute or two and give an extra minute to see who else will join us this afternoon. So hopefully more people will join us in the next couple of minutes. But as you have seen, I have posted a link with our lecture recordings of last week and what this week's also will be, as well as previous years' lecture recordings that I made. So before we start today, we're going to talk about light and telescopes. But to put things into perspective, I want to show you two quick videos.
I talked a lot about observing the sky with your eyes, just simply going out and seeing what you can see. It's pretty amazing what you can learn just by doing that, and of course, that's all we humans could do for thousands of years. But now we can do better. We can use telescopes. The first person to invent the telescope is lost to history. Despite common knowledge, Galileo did not invent them. He wasn't even the first person to point one at the sky or the first person to publish results, but he was a loud and persistent voice over the years, and his amazing string of discoveries using his crude instrument landed him firmly in the history books. Aggressive self-marketing sometimes pays off. You might think the purpose of a telescope is to magnify small objects so we can see them better. That's how a lot of telescopes are marketed, but to be honest, that's not exactly the case. If you want to be really general, the purpose of a telescope is to make things easier to see, to make the invisible visible, and to make the things already visible visible more clearly. A telescope works by gathering light. Think of it like a bucket in the rain. The bigger the bucket, the more rain you collect. If your bucket is big enough, you'll get plenty of water even when it's only sprinkling out. In the case of a telescope, the bucket is an optical device like a lens or a mirror that collects light. We call this device the objective, and the bigger the objective, the more light it collects. Look at your eyes. Well, that's tough, so let's think about our eyes for a moment. They also work as light buckets, but they only collect light through our pupils, which even under the best of circumstances are less than a centimeter across, a very tiny bucket indeed. But we can do better. To extend the analogy, a telescope is like a bucket with a funnel at the bottom. All that light that it collects is then concentrated, focused, and sent into your eye. It turns a trickle of light into a torrent. The amount of light it collects depends on the area of the objective. That means if you double the diameter of the collector, you'd collect 4 times as much light, because the area of the collector goes up as the square of the radius. Make a bucket 10 times wider and you collect 100 times as much light. Clearly, as telescopes get bigger, their ability to show us faint objects increases enormously. In fact, that was one of Galileo's first and most important discoveries. Stars that were invisible to the naked eye were easily seen through his telescope, even though it only had a lens a few centimeters across. Those faint stars didn't emit enough light for his eyes to see them, but when he increased his collecting area with a telescope, they popped into visibility. The primary way telescopes work is to change the direction light from an object is traveling. I can see a star with my eye because light from that star is sent in my direction, into my eye. But most of that light misses my eye, falling to the ground all around me. light, bounces it around, and then channels it into my eye. When the very first telescopes were built, this changing of the direction of light was done using lenses. When light goes from one medium to another, say from going through air to going through water or glass, it changes direction slightly. You see this all the time. A spoon sitting in a glass of water looks bent or broken. The spoon is doing just fine, but the light you see from it is getting bent, distorting the image. This bending is called refraction. The way light bends depends on what's bending it, like water or glass, and the shape of the object doing the bending. It so happens that if you grind a piece of glass into a lens shape, it bends or refracts the incoming light in a cone, focusing it into a single spot. It's a light funnel. This refraction has a couple of interesting results. For one thing, the light from the top of a distant object is bent down and the light from the bottom is bent up. When this light comes to a focus, it means you see the object upside down. It also flips left and right, which can be a little disconcerting and takes getting used to when you're using a refracting telescope. For another thing, the lens can magnify the image. That's again because the light is bent and the image created of an observed object can appear larger than the object does by eye. It depends on a lot of factors, including the shape of the lens, the distance of the object, and how far away the lens is. But in the end, what you get is an image that looks bigger. That has obvious advantages. A planet like Jupiter is too far away to see as anything other than a dot to the eye, but a telescope makes it appear bigger, and details can then be seen. When Galileo and other early astronomers pointed their telescopes at the sky, multitudes were revealed. Craters on the moon, the phases of Venus, Jupiter's moons, the rings of Saturn, and so much more. The universe itself came into focus. When astronomers talk about using a telescope to make details more clear, they use a term called resolution. This is the ability to separate two objects that are very close together. You're familiar with this. When you're driving on a road at night, a distant car coming toward you appears as a single light. When it gets closer, the light separates out, resolves into two headlights. A telescope increases resolution, making it easier to, say, split two stars that are close together, or to see details on the moon's surface. The resolution depends in part on the size of the objective. In general, the bigger the telescope objective, the better your resolution is. Resolution is more useful than magnification when talking telescopes. Fundamentally, there's a limit to how well your telescope resolves two objects, but there's no limit to how much you can magnify the image. If you magnify the image beyond what the telescope can actually resolve, you just get mush. Refracting telescopes are great, but they suffer from a big problem. Big lenses are hard to make. They get thin near the edge and break easily. Also, different colors of light bend by different amounts as they pass through the lens. So you might focus a red star, say, and a blue one will still look fuzzy. No less a mind than Isaac Newton figured a way around this. Use mirrors. Mirrors also change the direction light travels. And if you used a curved mirror, you can also bring light rays to a focus. Telescopes that use mirrors are called reflectors. The advantages of reflectors are huge. You only have to polish one side of a mirror, where a lens has two sides. Also, a mirror can be supported along its back, so they can be manufactured much larger, more easily, and for less money. Although there have been many improvements made over the centuries, most big modern telescopes at their heart are based on the Newtonian design. And in fact, no large professional-grade telescopes made today have a lens as their objective. Nowadays, it's all done with mirrors. And that brings us to this week's aptly named Focus On. The most common question I'm asked, besides, hey, who does your hair, is, hey Phil, what kind of telescope should I buy? It's a legitimate question, but it's very difficult to answer. Imagine someone walked up to you and asked, what kind of car should I buy? That's impossible to answer without a lot more information. Same for telescopes. Do you want to look at the moon and planets, or fainter, more difficult to spot galaxies? Are you really devoted to this, or is it more of a pastime? Is this for a child or an adult? These questions are critical. Most small scopes are refractors, which are good for looking at detail on the moon and planets. They tend to magnify the image more than reflectors do. But they're tricky to use because they flip the image left and right and up and down. Bigger scopes are good for fainter objects, but are more expensive and can be difficult to set up and use. I hate hearing about a scope that just collects dust because it was bought in haste. So here's what I recommend. Find an observatory, planetarium, or a local astronomy club. They're likely to have star parties, public observing events, where you can look at and through different kinds of telescopes. Their owners are almost universally thrilled to talk about them. As an astronomer, I can assure you that the problem with astronomers isn't getting them to talk, it's shutting them up. So you'll get lots of great first-hand advice and experience. Also, I usually recommend getting binoculars before a telescope. They're easy to use, fun to use, easy to carry around, and you can get good ones for less money and still see some nice things. Even if you decide not to get more into astronomy as a hobby, they can also be used during the day on hikes and for bird watching. I have a couple of pair of binoculars and I use them all the time. There's a third aspect of telescopes that's very important. Beyond resolution and making faint things easier to see, they can literally show us objects outside of the range of colors our eyes can see. In the year 1800, William Herschel discovered infrared light, a kind of light invisible to our eyes. In the time since, we've learned of other forms of invisible light: radio, microwave, ultraviolet, X-rays, and gamma rays. Astronomical objects can be observed in all these flavors of light if we have telescopes that are designed to detect these flavors of light. Radio waves pass right around normal telescopes, ones that we use to observe visible light. X-rays and gamma rays pass right through them as if they aren't even there. But we're smart, we humans. We learned that giant metal dishes can and will bend radio waves and can be formed just like gigantic Newtonian mirrored telescopes. In fact, different forms of light need different kinds of telescopes. And once we figured out how, we've built them. We can now detect cosmic phenomena across the entire spectrum of light, from radio waves to gamma rays, and have even built unconventional telescopes that detect subatomic particles from space as well, such as neutrinos and cosmic rays. Because of this, we've learned far more about the universe than Galileo could have imagined. And we're in the midst of another revolution too. The actual biophysics is complicated, but in a sense, our eyes act like movie cameras, taking pictures at a frame rate of about 14 images per second. That's a short amount of time. Photographs, though, can take far longer exposures, allowing the light to build up, allowing us to see much fainter objects. The first photographs taken through a telescope were done in the 1800s. This has led to innumerable discoveries. For example, in the 20th century, giant telescopes with giant cameras revealed details in distant galaxies that led to our understanding that the universe is expanding, a critically important concept that we'll dive into later in the series. And now we have digital detectors, similar to the ones in your phone camera, but far larger and far more sensitive. They can be dozens of times more light sensitive than film, able to detect in minutes objects that would have taken hours or more to see using film. These digital cameras can also be designed to detect ultraviolet light, infrared, and more. We can store vast amounts of that data easily on computers and use those computers to analyze that huge ocean of information, performing tasks too tedious for humans. Most asteroids and comets are discovered using autonomous software, for example, looking for moving objects among the tens or hundreds of thousands of fixed stars in digital images. This has also ushered in the era of remote astronomy. A telescope can be on a distant mountain and programmed to scan the sky automatically. It also means we can loft telescopes into space, above the sea of air in our atmosphere that blurs and distorts distant faint objects. We can visit other worlds and send the pictures and data back home, or put observatories like the Hubble Space Telescope into orbit around the Earth and have it peer into the vast depths of the universe. I would argue that the past century has seen a revolution in astronomy every bit as important as the invention of the telescope in the first place. In the early 17th century, the entire sky was new, and everywhere you pointed a telescope, there was some treasure to behold. But with our huge telescopes and incredibly sensitive digital eyes now, that's still true. We learn more about the universe every day, just as we learn that there's more to learn every day too. That's one of the best parts of being an astronomer. The universe is like a jigsaw puzzle with an infinite number of pieces. The fun never ends. And remember, even with all the wonders revealed by telescopes, your eyes are still pretty good instruments too. You don't need big fancy equipment to see the sky. The important thing is to go outside. Look up. That's fun too. Today you learned that telescopes do two things: increase our ability to resolve details and collect light so we can see Hey, Phil Plait here, and this is Crash Course Astronomy. In last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint. Light is a wave. It took centuries of thought and experiments to figure that out, and to also figure out that, at its most basic, light is a form of energy. It travels in waves, similar to waves of water in the ocean, except with light, the things doing the waving are electric and magnetic fields. Literally, Light is a self-contained little bundle of these two fields intertwined. That's why we call light electromagnetic radiation. The details of this are very complex, but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength as well, and this may be its single most important feature. That's because the energy of light is tied to its wavelength. Light with a shorter wavelength has more energy, and light with a longer wavelength has less energy. And our eyes have a really convenient way of detecting these different energies. Color. What you think of as the color violet is actually light hitting your eye that has a short wavelength. Red light has a longer wavelength, about twice the distance between crests as violet light. All the colors in between, orange, yellow, green, blue, have intermediate wavelengths. This spread of colors, wavelengths, is called a spectrum. Over millions of years, our eyes have evolved to detect the kind of light the sun emits most strongly. Well, that makes sense. That makes it easier for us to see. We call this kind of light visible light. But that's just the narrowest sampling of all the different wavelengths light can have. If light has a slightly shorter wavelength than what our eyes can see, it's invisible to us, but it's still real. We call that ultraviolet light. Light with shorter wavelengths than that fall into the X-ray part of the spectrum, and light waves with the shortest wavelengths of all are called gamma rays. At the other end, light with slightly longer wavelengths than the reddest color we can see is called infrared light. Light waves longer than that are called microwaves, and those with the longest wavelengths of all are called radio waves. These different groups don't really have hard and fast definitions. Just think of them as general guidelines. But together, we call all of these different kinds of light the electromagnetic, or EM, spectrum. And remember, energy goes up when the wavelength gets shorter. So ultraviolet light has a higher energy than violet, X-rays have a higher energy than that, and gamma rays have the highest energy of all. Infrared light has lower energy than red light, microwaves lower than that, and radio waves have the lowest energy. When you look at the whole EM spectrum, you'll probably notice that we really do only see a teeny little sliver of it. Most of the universe is invisible to our eyes. That's why we build different kinds of telescopes, to detect the kind of light our eyes can't detect. They let us see a lot of stuff that otherwise we'd never notice. So you might be asking, how is light made? Well, one of the most basic properties of matter is that when you heat it up, it gains energy, and then it tries to get rid of that energy. Since light is energy, one way to get rid of energy is to emit light. Another important property of matter is that the kind of light an object emits depends on its temperature. An object that's hotter will emit light with a higher energy, that is, a shorter wavelength. Cooler objects give off light with a longer wavelength. You may have seen this in action. Heat up an iron bar and it starts to glow red, then orange, then yellow as it gets hotter. The color, the wavelength of light emitted, changes as the bar heats up. Astronomers use a shorthand for this. We say that light with a shorter wavelength is bluer and light with a longer wavelength is redder. Don't take this literally. We don't really mean more blue or more red, just that the wavelengths are decreasing or increasing. So in this lingo, ultraviolet light is bluer than blue and X-rays are bluer than ultraviolet. So objects that are more energetic, that have a higher temperature, are bluer than cooler, redder objects. This rule of thumb works really well for dense objects like iron bars and stars. Even humans. You emit light, but it's in the far infrared, well beyond what our eyes can see. There are less dense objects in space too, like gas clouds, and the way they emit light is different. To understand that, we have to zoom in on them, way, way in, and look at their individual atoms. And to understand that, we need to take a brief diversion into atomic structure. Atoms are the building blocks of matter. In general, atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive electric charge, electrons a negative charge, and neutrons are neutral. Protons and neutrons are much more massive than electrons and occupy the centers of atoms in what's called the nucleus. Electrons whiz around the nucleus, their negative charge attracted by the proton's positive charge. The type of atom depends on how many protons it has in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, and so on up the periodic table of elements. It's common to think of the electron as orbiting the nucleus, like a planet orbits the sun, but that's not really the case. The real situation is fiendishly complex and involves pretty hairy quantum mechanics, but in the end, we're allowed to occupy very specific volumes of space around the nucleus, and those depend on the electron's energy. Think of these like stairs on a staircase, where the landing is the nucleus. When you walk up the stairs, you have to use energy to go up. And when you do, you have to go up a whole step at a time. If you don't have the energy to get to the next step, you can't move. You can be on the first step or the second step, but you can't be on the 1.5 step. There isn't one. Electrons are the same way. They whiz around the nucleus with a very discrete amount of energy. If you give them an additional precise amount of energy, they'll move up to the next energy level, the next step. But if you give them the wrong amount, they'll just sit there. The opposite is true as well. Electrons can be in a higher energy state, up on a higher step, and then give off energy when they jump down. The amount they give off is exactly the same amount needed to get them to jump up in the first place. How do they get this energy? Light. If light hitting the atom has just the right amount of energy, the electron will absorb it and jump up. It can also jump down and emit light at that energy too. An electron can also jump 2 steps or 3 or whatever, but it needs exactly the right energy to do it. But as I said earlier, energy and wavelength are the same thing, and that's equivalent to color. So when an electron jumps up or down, it absorbs or emits a very specific color of light. Not only that, but the steps are different for different atoms. To stick with our analogy, it's like different atoms are different staircases with different heights between the steps. So when an electron jumps down a step in a hydrogen atom, it emits a different energy, a different color of light than an electron jumping down in a helium or calcium atom. And this is the key to the universe. Because different atoms emit different colors of light. If we can measure that light, in principle, we can determine what an object is made of, even if we can't touch it, even if it's a bazillion light years away. And we can. Can you tell the difference between these 2 squares? They're a very slightly different shade of red. Your eye probably can't tell the difference, but a spectrometer can. This is a device that can precisely measure the wavelength of light and can, for example, distinguish light emitted by a hydrogen atom from light emitted by helium. When you hook one of these spectrometers up to a telescope, you can figure out what astronomical objects are made of. In the case of thin gas clouds in space, the atoms are basically floating free, rarely bumping into one another. The atoms emit those individual colors of light, allowing us to identify them. Unlike dense stars, the color of the thinner gas depends more on what's in it than its temperature. And this is how we learned what the universe is made of. Stars and gas clouds in space are mostly hydrogen, with some helium and heavier elements thrown in. Jupiter has methane in its atmosphere, Venus carbon dioxide. Everything in the universe has its own mix of ingredients, like cakes at a bakery. With spectroscopy, we can taste them. But wait, there's more. You're probably familiar with the Doppler effect, the change in pitch when, say, a motorcycle goes by. In sound, the wave defines the pitch. Higher tones have shorter wavelengths and lower tones longer wavelengths. When the motorcycle is headed toward you, the sound waves get compressed, causing the pitch to rise. After it passes you, the pitch drops because the wavelengths get stretched out. The same thing happens with light. If an object is headed toward you, the wavelength of light from the source gets compressed, shorter. We say the light is blue shifted. If it heads away, the wavelength gets longer and it's red shifted. Apply that to a spectrum, and by measuring that shift, we can tell if an object is moving toward or away from us. Here's a teaser. This becomes super important later when we talk about galaxies. Spoiler alert, the universe is expanding, and it's this redshift that allowed us to figure that out. And that's still not the end of it. With other spectroscopic techniques, we can determine if an object is spinning and how fast, whether it has a magnetic field and how strong it is, and even how massive and dense an object is. A vast amount of the fundamental properties of astronomical objects can be found just by dissecting their light into individual colors. Almost everything we know about the universe comes from the light objects in it give off. Pictures of astronomical objects show us their structure, their beauty, and hint at their history. But with spectra, we can examine their blueprints. Today you learned that light is a form of energy. Its wavelength tells us its energy.
So hopefully that provides an overview of what we will be discussing in today's lecture. So for today, we are going to talk about what is light in telescopes, the radiation coming from space, what observatories do we have, what's the difference between airborne and space observatories, and what are some of the astronomical instruments and techniques that we make use of to study objects from space. So I want to start off with a quote. The strongest thing that is given to us to see with a telescope. Someone in every town seems to me owes it to their town to keep one. So at the end of this lecture, we will be able to answer the following questions. The first question is, what is light? The second question is, how do telescopes work? The third question is, what are the powers and limitations of telescopes? Fourthly, what kind of instruments do astronomers use to record and analyze light gathered by telescopes? And lastly, why must some telescopes be located in space? So the science of astronomy that we've talked about is an observational astronomy or an observational science. Therefore, we observe what we are seeing. But the only problem is we cannot visit the objects we are observing because they are so far away. So therefore, the only way available to us to study them is by making use of telescopes. So the quest of astronomers is to study light from the sun, planets, moons, asteroids, comets, stars, nebulae, and galaxies, and extract information about their nature. Most celestial objects are very faint sources of light. So large telescopes are built to collect the greatest amount of light possible. Some types of telescopes gather light that is invisible to the human eye, but all telescopes work by the same basic principle. Some telescopes are used on Earth's surface, but others must go high in Earth's atmosphere, or even above the atmosphere into space to work properly. This chapter focuses on telescopes, instruments, and techniques that is used to analyze light for astronomical research. So where we are in modern astronomy, we don't, well, in these modern days, we don't map constellations, look at the face of the moon, or try to observe new things, but we try to analyze the light from these objects by making use of specialized instrumentation and try to see how these objects work. What are the fundamental laws governing these objects? And how do they evolve over time? So you're all probably familiar of the story that light is a wave and a particle. So when you admire the colors of a rainbow, you are seeing an artifact of light acting as a wave. But when you see a picture of the same rainbow, the light acts like particles hits the camera's detectors. So light has both wave-like and particle-like properties. And how it behaves depends partly on how you treat it. So I've shown this image in our opening lecture 3 weeks ago. But this is the electromagnetic spectrum. So as you can see, normal visible light forms part of the electromagnetic spectrum. So here we can see, let me get the pointer out, we have our radio waves on one end, and we have our high frequency on the other end, which is gamma rays. And visible light forms a small part of that section. So telescopes is usually designed to detect a certain range of frequencies. So radio telescopes is usually designed to do a bit of infrared all the way to long radio waves. Optical telescopes does visible light and a little bit of infrared. And then other high frequency observatories are designed to look at UV, X-rays, and gamma rays. So some people are wary of the word radiation, but that involves a common misconception. Radiation refers to anything that radiates from a source. Dangerous high-energy particles emitted from radioactive atoms are also called radiation. And you have learned to be concerned when you hear that word. But like all electromagnetic radiation, spreads outward from its origin, so you can correctly refer to light as form of radiation. Electromagnetic radiation travels through space at a speed of light, which is 3 times 10 to the power 8 meters per second, so roughly 300,000 meters per second, symbolized by the letter C. This is commonly referred to as the speed of light, but in fact, the speed of all types of electromagnetic radiation is the same. So you are all probably familiar with these equations from high school, correct? So in these equations, we have lambda, which is the wavelength. So over here, we have c, which is the speed of light, and we have v. So there's not actually v, it's pronounced nu. So nu is frequency. So I don't like this form of the equation. I like to present it as F equals C over lambda, but it's just a donation. So the textbooks like to use nu, so we are going to use nu to stick to conformity along with the textbook. On the moon, where there is no air, there can be no sound. In contrast, light is made up of electric and magnetic fields that can travel through empty space. In other words, unlike sound, light does not require a medium and can travel through a perfect vacuum. Although electromagnetic radiation can behave as a wave, it can also behave as a stream of particles. A particle of electromagnetic radiation is called a photon. You can think of a photon as a packet of waves. The amount of energy a photon carries is inversely proportional to its wavelength. Notice in the equation that there is a relationship between the energy of a photon, which is a particle property of light, and the wavelength lambda, which is a wave property. The inverse proportional means that lambda gets smaller, energy gets larger, so shorter wavelength photons carry more energy, and longer wavelength carries less energy. So one thing is, where are my sci-fi fans? So if you watch Star Trek, Star Wars, doesn't matter which sci-fi show or movie you watch, you always see these spectacular space battles, and you hear the sounds of the lasers or the phasers they're firing, but that is actually unrealistic. Do you guys know why? Yes, sound can't travel in space. Sound needs a medium to propagate through. And in space, there's no medium to propagate through. So if there's a spectacular space battle, we won't be able to hear anything. So that's just something interesting. And also, you see those spaceships doing these maneuvers, banking left and right. In space, that is also not possible, because to move left and right and to bank, you need air resistance. So that's just a flaw in all sci-fi shows, perhaps, but that is just how physics works. So that's just a side note and something interesting. So when we look at the electromagnetic radiation, and we can look at the EM spectrum, So let me get something out to draw with. Let's use this color. So this is the entire EM spectrum. So our atmosphere absorbs a lot of the spectrum. So if we have our ground over here, not all the EM waves, so EM short for electromagnetic rays, hits the surface. So here we can see high energy gets absorbed by the atmosphere. Microwaves in infrared gets absorbed by the atmosphere, and here AM, FM also. So the only places we can put telescopes to do observations is in the visual wavelength. So this is a bad color. So that means we can observe visible light, a little of ultraviolet, and a little bit of infrared. And the other part we can do observations is the radio part of the spectrum, so radio waves, because the atmosphere is opaque to those frequencies. So that means if we want to observe the other, we need to be at high mountain ranges, that we are above the water vapor level in the atmosphere. So meaning if we want to observe X-rays, we need to be above this level in the atmosphere. Same with AM radio or in space. So that is just to put in perspective of why we build certain telescopes on the ground, and why we build certain telescopes on mountain ranges, and why some is in orbit. Does everyone understand that? Everyone happy? Awesome. So the average wavelength of visible light is about 0.005 millimeters. So roughly 50 light waves would fit end to end across the thickness of a sheet of household plastic wrap. Scientists usually give the wavelength of light using nanometer units, equal to 1/1000th of a meter. Another unit that astronomers commonly use is called the angstroms. This is a hint for the tests and exams. I can perhaps ask you, what is the definition of an angstrom? So remember, another unit that astronomers use is called the angstrom, named after the Swedish astronomer Anders Jonas Angstrom. And 1 angstrom is 1/10th of a nanometer. So the wavelength of visible light ranges from about 400 to 700 nanometers, or 4,000 to 7,000 angstrom. Only visible light, some shorter wavelength infrared, and some radio waves reach Earth's surface through wavelength bands called atmospheric windows. Obviously, if you wish to study the universe from Earth's surface, you have to look through one of these windows. So a bit of a side note, these windows we can look through. One of my Canadian colleagues, which is now in Canada, he calls these two spots the watering hole, because it penetrates through water vapor in the atmosphere. So that's something just he nicknamed. So astronomers build telescopes to collect light for analysis from distant faint objects. This requires very large telescopes plus careful optical and mathematical engineering work. You can understand these ideas more completely by learning about 2 types of telescopes and their relative advantages and disadvantages. So light can be focused into an image in one of 2 ways. Either a lens refracts or bends light passing through it, or number 2, a mirror bounces the light off the surface. So when we have 2 optical telescopes, these are the 2 primarily designed. So in image A, you can see the incoming light ray coming through. It goes through a lens and it gets focused. But we'll see the image is upside down. And then we also get in image A, we can see the light rays hits a mirror. The mirror reflects the light to a focus point, and you can see the image is upside down. So what is image A? So it's image A. What kind of telescope is it? I want to ask you guys. Is it refracting or reflecting? So both of them show. So the one above is refracting. The one below is reflecting. So let me get this out. So this is a refracting telescope. This is a reflecting telescope. And what's also important to denote is the focal length that we have here in our telescopes. So the focal length is distance from the lens or the mirror to the point where parallel rays or light form very distant objects come into a focus. So both of these telescopes have its advantages, and we also designed telescopes with certain focal lengths in mind. So some focal lengths are better to focus planets, some is better to focus more deep space objects. So it all depends on what we want to observe and which telescope is the best for that. So these two ways to manipulate light corresponds to two astronomical telescope designs. The refracting telescope uses a lens, and the reflecting telescope uses a mirror to gather and focus light. The main lens in a reflecting telescope is called a primary lens, and the main mirror in a reflecting telescope is called a primary mirror. And both kinds of telescopes form an image that is small, inverted, and difficult to observe directly. So a lens that is called the eyepiece normally is used to magnify the image and make it convenient to view. So Galileo was the first person to systematically record observations of celestial objects using a telescope, beginning almost exactly 400 years ago. In 1610, Galileo's telescope was a refractor. You also learned about the amazing range of Isaac Newton's scientific work, and among his accomplishments was the invention of the reflecting telescope. So these are the two different designs of how it works. So as we can see in the telescope on the left, we have incoming light. It hits a primary lens, and that lens focuses the image right here. And then we have another lens in the eyepiece that magnifies the image we are looking at. So a refracting telescope. Then in a reflecting telescope, we would have a primary mirror. The mirror reflects the light back up to a secondary mirror, and then from the secondary mirror it gets reflected into the focal point where our eyepiece is. So one thing between these two different designs is, with a reflecting telescope, you have a very short focal length. So it all depends what you want to do and what design you want to follow. So reflecting telescopes suffer from a serious optical distortion that limits their usefulness. When light is refracted through a glass, shorter, please explain focal length, sir. Okay, going back. So here we can see the focal length. So let me just clear the annotations. So here we can see the focal length is the distance it takes for an image to be formed and to focus. So, for example, in general, in a refracting telescope, the focal length will be longer than in a reflecting telescope. So it means the focal length, the distance from the lens or the mirror where the image is focused, that is the focal length. And depending what objects you observe in space, sometimes you want a shorter focal length, sometimes you want a longer focal length. Who of you are photography fans, or who of you does photography as a hobby? Okay, one hand raised. So if you do photography, your focal length is also very important. So when you do a photography, sometimes you want shorter focal lengths if you want to take pictures up close of certain things. So a good example is if you do micro photography. So meaning micro macro when you're doing, for example, when you take pictures of up close pictures of insects or plants or flowers. But in some cases, you want to take images of things that's far away. So let's say, for example, you are in a game reserve and you want to take a picture of an elephant that is far away. Then you need a bit of a longer focal length to get a better image. Does that explain what focal length means? Awesome. So when we're looking at refracting telescopes, it has a bit of a problem. So when light is refracted through glass, shorter wavelength light bends more than longer wavelengths. So for example, blue light having shorter wavelengths comes to a focus closer to the lens than does red light. That means that if you focus the eyepiece on blue image, the other colors are out of focus. And if you see a colored blur around an image, if you focus instead on a red image, all the colors except red are blurred and so on. So this separation is called a chromatic aberration. So this is also a question I like to ask in a semester test and exam is what is chromatic aberration or what causes chromatic aberration? So telescope designers can grind a telescope lens with two components made of different kinds of glass and thereby bring two different wavelengths to the same focus. That does improve the image, but these so-called achromatic lenses are not totally free of chromatic aberration. Even though two colors have been brought together, the others are still out of focus. So if we visualize this, so here we have just a normal single lens. So the blue light is being brought into focus first and the red light further. So if we now focus our lens, say for example on this part over here, that means the red colors will be out of focus. So if we focus on the red colors of the image, that means the other colors will be out of focus. So when we add an achromatic lens, that means the two different pieces of lens are made of different materials, and some of them has grooves, some of them is a bit more smoother. You can bring these 2 points closer together. So it's much closer compared to the image above, but there are still drawbacks that they can be a bit of out of focus, but this is one technique to help us focus our image better. So telescopes that collect visible light are called optical telescopes. Like visible light, radio waves from celestial objects can penetrate Earth's atmosphere and reach the ground. Astronomers gather radio telescopes that resemble a giant TV satellite dish. It is technically very difficult to make a lens that can focus radio waves. So all radio telescopes, including small ones, are reflecting telescopes. The dish is the primary mirror. So here are two examples of it. So image A is the Gemini North Optical Telescope. So here below we can see the primary mirror. Here is the secondary mirror, and then light rays get reflected down in here where the instrumentation is. On the image on the right is the Green Bank Radio Telescope. So here we can see our primary reflector. So the incoming radio waves get reflected up to the subreflector, which is at a point over there, and then into the receiver. So I explain chromatic and achromatic, but slower. Okay. Let me clear this again. So with chromatic lenses, a normal lens is always chromatic, meaning shorter wavelengths of light is focused first, and then longer wavelengths of light is focused a bit later on. So that means when we compare the two, here we can see blue light is focused, here we can see red light is focused. But that brings us or creates a bit of a problem when we observe or look or try to focus a object. So if we focus on the blue part of an image, that means the blue part will be in focus, but the red part will be out of focus and a bit blurry. So we can try and focus on the red part, but then the bluish colors will then be blurry and out of focus. And that is what we called chromatic aberration. So one way to fix it is by making use of achromatic lenses. So achromatic lens is two different, we're not using one single lens. It's actually two lenses with each with a unique design that is stacked and put onto one another. So now what that happens is that it tries to bring the focus point of the blue and the red closer to one another so that you can try and focus your lens on both of them, that you don't get the blurry image. But as you can see, there are still a little bit of a distance between them, so it's working, but it's not 100% perfect. Does that answer the question better? Awesome. So astronomers use the term seeing to refer to the amount of image blurring due to atmospheric conditions. A related phenomenon is the twinkling of the stars. Star twinkles are caused by turbulence in Earth's atmosphere. And a star on the horizon, where you look through more air, will twinkle and blur more than a star overhead. And that is also where we can distinguish between a star and a planet. So a star, because it's so far away, is much less light entering the atmosphere. So that means turbulence in the atmosphere will distort it a lot more, and therefore it will twinkle. But a planet, the light coming from a planet is much closer to Earth, this much more intense, and therefore the turbulence in the atmosphere will have a bit less of an effect of it, and therefore it won't twinkle. So that is just something interesting. So here in the image A on the left, stars are so far away that the images are points. But a wave-like characteristic of light causes each star's image to be surrounded with diffraction fringes, much magnified in these computer models. Then in image B, two stars close to each other have overlapping diffraction fringes and become impossible to detect separately. So one thing to take in consideration with our telescopes is the bigger the opening, so the bigger, where's something to draw, so the bigger this opening is, the more light we can gather. And the more light we can gather, the clearer and more detailed our image is. You can think about it as a bucket collecting rainwater. If we have a larger bucket, we can collect more water. Same thing with a telescope. So the larger the opening, the more light we can collect, and the clearer our image will be. So in this image, we can see image A on the left is from a galaxy, an image recorded on a night of poor seeing, meaning there was a lot of turbulence in the atmosphere. And then the image on the right is from the same galaxy, but when the atmosphere above the telescope was more stable. So atmospheric stability plays a very, very big role. So telescopes are usually built in areas that is as dry as possible and as high as possible. Can you hear me now? Is this a bit better? So what that means is, if telescopes are built in places where the atmosphere is as dry as possible and you as high as possible to minimize the atmospheric instability. So that's why Sutherland is chosen to host all the optical telescopes in South Africa. So in Sutherland, you usually get about 300 nights of perfect viewing conditions out of 365 nights. So that is why Sutherland was specifically chosen. So this is a question I also like to ask in the tests in the exam. And this is basically just to compare the powers of a telescope. So let's go through it. So you can see it's just plug and play. So the light gathering power of a telescope is proportional to the area of the primary mirror or lens. A primary with a large area gathers large amounts of light. So an area of a circle lens of mirror of diameter, d is pi multiplied by d over 2 squared. So compare the relative light gathering powers. So LGPs is light gathering powers of two telescopes, A and B. You can calculate a ratio of the areas of their primaries, which is the ratio of the diameter squared. So this is the only equation that you need to know for this example is. So on this side is the light gathering powers, there's a ratio, and this is diameter of telescope A and diameter of telescope B squared. So if I give you different scenarios, I'll give you the light gathering power of A, the light gathering power of B, then you can calculate diameters, or the other way around. But please go through this example on your own time. It's straightforward, plug and play math. So astronomers avoid cities because light pollution can brightening of the sky by light scattering from artificial outdoor lighting can make it impossible to see faint objects. So radio astronomers face a problem of radio interference comparable to visible light pollution. Weak radio waves from the cosmos are easily drowned by human-made radio noise. Everything from automobiles with faulty spark plugs to poorly designed communication systems. A few narrow radio bands are reserved for astronomy research, but even those are often contaminated by stray signals. To avoid that noise and have the radio equivalent of a dark sky, astronomers locate radio telescopes as far from civilization as possible, hidden in mountain valleys or in remote deserts. They are able to study the universe protected from humanity's radio output. And that is also why I said in our opening lecture, with radio telescopes, there is no Bluetooth, no Wi-Fi, no microwaves around to stop interference on these telescopes. So for most of the 20th century, astronomers faced a serious limitation on the size of astronomical telescopes. Telescope mirrors were made thick to avoid bending that would distort the reflecting surface. But those fixed mirrors were heavy. The 5-meter mirror on the Mount Palomar weighs 14.5 tons. And these old-fashioned telescopes were not only big and heavy, but also expensive. So today's astronomers have solved these problems in a number of ways. So if you think about it, when you try to build one big telescope, first of all, it becomes expensive, and secondly, the engineering becomes more difficult because you have now a big, heavy structure that you need to move. So a few ways where this can solve is conventional design reflecting telescopes use large, solid, heavy mirrors to focus starlight to a prime focus, or by using a secondary mirror to a Cassegrain focus. Other telescopes have a Newtonian focus or a Schmidt-Cassegrain focus. Secondly, telescopes must have a sidereal drive to follow stars. An equatorial mount with motion around the polar axis is the conventional way to provide that motion. Today, astronomers can build simpler, lighter-weight telescopes on alt-azimuth mounts that depends on computers to move the telescope so that it follows the apparent motion of stars, as Earth rotates without having an equatorial mount and polar axis. So traditionally, before we had powerful computers, before we had computers in our homes, telescopes made use of mechanical drive, and those mechanicals were equatorial and polar axis mounts. So meaning the telescope moved as the Earth rotated, so equatorial, and also up and down in the polar directions. But now it's not needed. So now with computerized or computers available, we can move a telescope anywhere we like with electrical drives and not mechanical drives, and that makes it much simpler. And then we also have active optics. So computer controlled of the shape of the telescope's main mirrors allow the use of thin, lightweight mirrors. So nicknamed floppy mirrors or segmented mirrors. I prefer to use the term segmented mirrors. Reduce the weight of the mirror, reduces the weight of the telescope, making it stronger and less expensive. Also, thin mirrors cool and reach a stable shape faster at nightfall, producing better images during most of the night. So here is how a modern telescope will work. So we will have our incoming light rays, we will have our primary mirror, here we will have our secondary mirror, and that will focus the light. And then with this primary mirror is usually segmented. And here also where we have our secondary mirrors, also where we will have our adaptive optics, but we will talk about that in a moment. So here we can see also the segmented mirror compared to a full-size mirror. That also helps a lot. So modern engineering techniques and high-speed computers have allowed astronomers to build and use new giant telescopes with unique designs as well. So some of these unique designs is the Very Large Telescope, the ESO, which mirrors are 8.2 meters in diameter. So here we can see only 12 of the 36 primary mirror segments have been installed at a time when this photo has been taken. Or here we can see the Large Binocular Telescope as well. And here are some future proposed telescopes. So the Giant Magellan Telescope, the 30-meter telescope, meaning it's 30 meters in diameter, so that will be one of the largest optical telescopes in the world. And then the European Extremely Large Telescope that has been constructing with 39 meters in diameter, which is huge for a telescope. And then we have modern telescopes. So you guys recognize this radio telescope. So question, sir, do reflective mirrors have a blind spot because of the smaller mirror? So sometimes mirrors have blind spots, but it's not due to the smaller mirror, but I will get to that in a moment. Optical radio telescopes has the exact same problem as well. But this is the Arecibo telescope that was in Puerto Rico. So this was the world's second largest telescope. It was built in a valley in Puerto Rico, and it was 300 meters across. Unfortunately, for the Arecibo telescope collapsed. Back in 2022, a tropical cyclone hit Arecibo in Puerto Rico, and the telescope took major damage. And before that damage could be assessed and repaired, a second storm hit the islands as well, and the telescope received even more damage and unfortunately collapsed. But one thing that we realize about telescopes is, let's take this one for example. Not this one. Let's see if we can get a better one for example. Let's go back a couple of slides to the Green Band telescope image. Okay, so the first question is, when you can see the radio telescope we have here, the Green Band telescope, we can see we tried to keep this surface as open as possible, And our secondary mirror that's up here is to the side. We call this a offset Gregorian telescope because it tries to not block the surface area of the telescope, meaning we can utilize more of the surface. But let's say, for example, how it was traditionally done a couple of years ago, we would have a few struts coming from all sides, and we have our sub-reflector there. But what we realize is the struts block a bit of the surface area, and we don't want that. So from the strut design, we now are moving over to a offset Gregorian design that you do not block the surface area of the telescope. We have the same thing with optical telescopes as well. So in this image, we try to put these struts in such a place that we don't block the primary mirror. So yes, with these struts, we do block it a little bit, but we try to minimize that as possible. So question, why do we find modern radio telescopes in isolated areas? It's like I said in our introductory lecture. We want radio telescopes as far as away from civilizations because cell phone signals, TV, Wi-Fi, Bluetooth, microwave ovens, radio, all causes interference on our radio telescopes. And we don't want that interference. We try to put them in as isolated regions as possible. And then in those isolated regions, we ban everything that can cause interference. So the Green Bank telescope, this one here, is in West Virginia, the United States. And it's in there's a 120-mile radius around the telescope where there's no radio, no television, no Bluetooth, no Wi-Fi, no microwave ovens to protect the telescope from interference. Does that answer your question? Awesome. So radio astronomy works under two disadvantages relative to optical astronomers: poor resolution and low signal intensity. Recall that resolving power of a telescope depends on the diameter of the primary lens or mirror and also on the wavelength of the radiation. At very long wavelengths, those of radio waves, the diffraction fringes are relatively large. And this means that images or maps from individual radio telescopes generally don't show such fine details as are seen in optical images. The second handicap radio astronomers face is the low intensity of radio signals. You learned earlier that the energy of the photon depends on its wavelength. Photons of radio energy have such long wavelengths that the individual energies are quite low. So the cosmic radio signals arriving on Earth are astonishingly weak. So 1 million to 1 billion times weaker than a signal from a commercial radio station. To get detectable signals focused on antenna, radio astronomers must build large collecting areas, either as a single large dishes or by combining arrays of smaller dishes. Even then, because radio energy from celestial object is weak, it must be strongly amplified before it can be measured and recorded. And something interesting about this as well is even the electronics on the telescopes causes interference. So the electronics is cooled as close to absolute zero to get electronic noise out. So the receivers on the radio telescope at Hadrell are kept at 12 degrees Kelvin. So that is roughly minus 260 degrees Celsius to get electronic noise out of the system. So ground-based telescopes, performance is limited by Earth's atmospheric turbulence and transparency. As we learn, there are sophisticated techniques that partly compensate for atmospheric seeing, but a telescope in space has no such problem and its resolution is defined only by diffraction. Also, a telescope on the ground must look through one of the two open atmospheric windows in the visible or radio parts of the electromagnetic spectrum. So most types of electromagnetic radiation arriving here from the universe, infrared, ultraviolet, X-rays, and gamma rays, do not reach Earth's surface because they are partly or completely absorbed by Earth's atmosphere. To operate at those blocked wavelengths, telescopes must go to high altitudes or into space. As you will learn in the next few chapters, objects that are cooler than stars, such as stars that are forming, emit infrared and radio radiation and relatively little visible light. In contrast, cosmic catastrophes such as exploding stars make mostly gamma rays and X-rays. Combining information from as wide a variety of wavelengths as possible allows astronomers to gain a more complete understanding of the universe. So one of the telescopes that was put in space is the Edwin Hubble Space Telescope, or the Hubble Space Telescope in short. And that was launched in 1990 and contains a 2.4 meter mirror. So the James Webb Telescope was recently launched, and it has a 6.5 meter telescope, providing more detail than Hubble. So here we can see the Hubble Space Telescope. Here is an artist's conception of the James Webb Telescope. We also have a few other space telescopes. So this is the Herschel Space Observatory. So this is just the atmospheric windows. But we also have airborne observatories. This is SOFIA of NASA's, the infrared observatory. So SOFIA was also retired last year because it reached end of life. But it was a Boeing 747, and it had a telescope in the back. We would get above the atmosphere where infrared is observed, and we can observe the stars. So this is the visual image of Jupiter, but in the right is an infrared image of Jupiter taken by SOFIA. So that is actually very, very cool. So with this, we also have other telescopes as well. So to observe X-rays, we need to be at high and dry places to detect X-rays on the ground, or we have to be in space. So another telescope or space telescope that just observes X-rays is called the Chandra X-ray Observatory, or the Chandra telescope for short. And Chandra currently is now booked 36 months in advance. So how it works on a telescope: if you want to observe something, you need to write a proposal. Your proposal is sent to the telescope, then a committee sits and decides if what you want to observe and the research you want to do is worthwhile. If it's worthwhile, you are assigned a X amount of time on the telescope to do your observations. So Chandra is currently booked 36 months in advance. So if you have a proposal that is accepted now, you will only get a chance to collect data with Chandra within 36 months. At Hydra, where I am, it's about 18 months in advance now. So with high energy astronomy, such as X-rays, for example, it is very difficult to detect because X-rays move basically through all material and you get stopped by lead and a few other things. So how do you focus X-rays on a detector where it usually moves directly through? So with that is, we have these specialized mirrors. And these specialized mirrors focuses the X-rays onto a detector, which is quite a unique design, and it works quite well. And then we also get gamma rays, so more higher energy. So one of the first gamma ray observatories was the Compton Gamma Ray Observatory, launched in 1991. And it mapped the entire sky at gamma ray wavelengths. The European Integral, so International Gamma Ray Astrophysics Laboratory satellite, was launched in 2002 and has been very productive in the study of violent eruptions of stars and black holes. The Fermi Gamma Ray Telescope, launched in 2008, is capable of mapping large areas of the sky to high intensity. So with this, we also have the HESS telescope in Namibia. The HESS telescope is also designed to do gamma ray observing, but gamma rays cannot reach the ground directly. But gamma rays can interact with particles in the higher atmosphere. So the telescope observed the interactions of the particles in the atmosphere, which is quite a clever design. So like I also said, our equipment is cooled to close as absolute zero as possible. So we usually make use of liquid nitrogen and liquid helium that is pumped through a system to cool down our electronics. So one thing is, if we look at the image from an object in space, it doesn't really tell us much. So one thing is that's quite a common misconception about astronomy is people think we just look at pretty images. We don't look at images. The images we use for public engagement, but we actually look at data coming from a telescope. So the raw data, that is not an image. But before we get to that, we usually had a photographic plate in the early 1900s, at the end of the 1800s. So a photographic plate, you can basically think of it as an X-ray sheet. So what happens is we have your X-ray sheet, and wherever there's a light shining on it, that is etched permanently into that place. So in the 1800s and early 1900s, those were used to do observations or to capture images. But now we use CCDs, so a charged coupled device, and that is what's in digital cameras and in your phone cameras. So usually when you speak about megapixel of the camera, it means the pixels on your CCD is bigger and more, and that means you can get a better image that you want to observe. So a good question I can ask for the semester test and the exam is, what is a CCD, for example? So when we look at infrared, astronomers use array detectors that are similar in operation as optical CCDs, but is designed at infrared wavelengths, and photometers are still used for measuring the brightness of celestial objects. So this is a good example of how one of these photographic plates, will look like. So here on the top left is a normal visual image. So an image in the bottom is a negative image, which is usually how a photographic plate will look like. But something interesting about this, and a point I want to make, is when we observe and putting data together, sometimes we don't care about the actual color. We can assign the data false colors. And the false colors, we can assign intensity and whatever we want to understand it better. To put that into perspective, if we look at a weather report, so this is the weather report in the US, we can say if it's a more purple color, there is more rain expected. And that is how we would use false color images. So for example, the Tycho supernova remnant, we can say the more yellow the color is, the more radio waves we get from that image. And the more bluish it is, the less radio waves. So you're all happy with the definition of false colors. Everyone happy with that definition? Awesome. So one thing that we do with optical and radio telescopes is we look at the spectrum, or in plural, spectra of objects. So we have a spectrometer, the device, and it creates a spectrograph of the object we are observing. So a spectrograph is basically the same principle of how a prism works. So visible light comes in, white light, and it's split into its primary colors. And that is what we call the spectra of visible light. with objects in all the electromagnetic spectrum, it has different spectra we can observe. And we will learn in a following lecture is we get emission spectra and absorption spectra. And each element and molecule in the universe has a unique spectrum. And therefore, when we observe objects in space, we know what the different elements and molecule spectra is, and therefore we can know what its composition is. So this is the observatory where I'm involved in, the Hartebeeshoek Radio Astronomy Observatory, or HARDRAO, that is just between Krugersdorp and Hartebeespoort Dam. So here you can see the big 26-meter telescopes, 26 meters in diameter. Here in the back you can see the 15-meter telescope. And it has a spectrometer that we use. This is the Green Bank Observatory, United States, the world's third largest telescope. It also has a spectrometer, but as you can see, it's much bigger and therefore it has a larger collecting area. So this is typically how a spectrometer will look like. It's just in this case, is an FPGA, so field programmable gate array, which is a type of processor which is very good at parallel computing. So you would get your signals coming from space, and then it is analyzed by making use of an FPGA or a GPU or a CPU. But in this case, it's an FPGA. So this is a methanol maser, the spectra of a methanol maser that was observed on the 26-meter telescope at HARDRAO. So this is what we call an emission spectrum. So we can see here a giant peak, and that peak is sitting at 6.6 gigahertz. So it means it's emitting energy at 6.6 gigahertz. And if we look at spectra in the lab of all elements and molecules, we know methanol as emission spectrum at 6.6 gigahertz. So therefore, we are looking at a methanol maser. So a few things that we can do with our telescopes to help our seeing conditions is adaptive optics. And this is also a question I like to ask, is what is adaptive optics? So you've already learned about active optics. So techniques to adjust the shape of the telescope optics slowly, compensating for effects in temperature as well as gravity. So an active optics is we can change the mirror of a telescope on the fly by making use of computers to focus different parts of the image better. So that is active optics. But now we have adaptive optics, and it is a more sophisticated technique used high-speed computers to monitor the distortion produced by the turbulence of the atmosphere and rapid alter some optical components to correct the telescope image. So in active optics, that is something like our abbreviation that we've seen. So we can design something active to help with the focus. But in adaptive optics, we can use computers to change the mirror on the fly to help focus our image. So here on this image A in the left, we can see our adaptive optics off and adaptive optics on, which is quite cool. And then one other thing we can do with our telescopes is interferometry. So one of the reasons astronomers build big telescopes is to increase the resolving power. And astronomers have been able to achieve very high resolution by connecting multiple telescopes together to work, in a sense, as if they comprised a single very large telescope. This method of synthesizing a virtual large telescope from two or more smaller telescopes is known as interferometry. So traditionally with a telescope is, the bigger you build it, the better. But the bigger you build it, the more expensive it becomes and the more complicated it becomes to move and the more difficult it is. So by making use of interferometry, you can build a few smaller telescopes and add their surface area together to create a larger telescope. So how it works is, for example, here we have our three telescopes, and then by making use of interferometry and interferometry math, we can create a virtual telescope that is the size of the distances between these telescopes, which is very, very cool. And that is the same principle how the VLA array in the US works. and as well as MeerKAT in South Africa, as well as the MeerKAT that will become the SK8 project. Then one other thing we can observe in astronomy is non-electromagnetic astronomy, and that is cosmic rays. And those are subatomic particles traveling through space at tremendous velocities. Almost no cosmic rays can reach the ground, but some of them smash into gas atoms in Earth's upper atmosphere. Then fragments of those atoms shower down to the ground. And those secondary cosmic rays are passing through you as you read a sentence. And other types of particles from space interact weakly and seldom with Earth's atoms. So huge detectors must be built to catch and count them. And detectors for some kinds of cosmic rays have been carried on balloons or launched into orbit, while others have been built deep underground. So do you guys know which instrument and facility this is? This is called the LIGO Observatory. Are you guys familiar with LIGO? So LIGO is built to detect gravitational waves. So I will show you in the next lecture a video on LIGO as well. But there are two of these facilities built in the US. The two furthest points from one another. So here you have the facility, and here you have a pipe or a tube that is 4 kilometers long, and another one on the other side it's 4 kilometers long at right angles to one another. What is interesting about this, 4 kilometers is so long that the Earth's curvature starts taking effect. So they have to build it extremely level. Then what you do is, with LIGO, this is a schematic of them. You have a laser, and then here is a mirror that splits the laser into two, and then you shine the laser into these 4 kilometer pipes down. So these two lasers, when they get split, are out of phase with one another. So when they come back, and you have a detector, another mirror over here, and it reflects it back. So when they're out of phase, they cancel each other out. So at a detector, we will see basically nothing, because we will have a, where can I get my white? Let me get the whiteboard out. We would have something like this. So here we will have our normal. So here we will have our normal laser, normal sinusoidal wave, but the other one is now out of phase. So that means it will look something like this. So when these two waves are added together, they are canceling each other out. But when you have two other waves again, and now let's say, for example, a gravitational wave goes through Earth, that means one of those tunnels, one of those legs, are stretched or compressed a little bit. So that means with stretching and compressing, these two waves will now all of a sudden be in sync. So that means you have a superposition on them, and that creates a combined larger laser beam. And that is how LIGO works to detect gravitational waves. And a Nobel Prize in Physics was given to this in, I think, 2019. So one of the things can cause gravitational waves is the merger of two black holes or two neutron stars hitting one another. So question, so wasn't this also something that Einstein predicted long ago before we were able to prove it? Yes, Einstein predicted it and it was finally measured. So this is the LIGO Observatory, and this is a non-electromagnetic astronomy. But I will show you a video on LIGO in our next lecture. So, ladies and gentlemen, this was today's lecture. Do you have any questions? So I assume there's no questions. So if you have no questions, you are all more than welcome to log off. Remember, next week's classes will all be online. Unfortunately, I have another commitment also for the week, but I will see you online for next week, Monday and Tuesday. So question, what about the James Webb Telescope? That is a reflection telescope. So if there's no further questions, I'm also going to log off. I will also upload the video immediately now when I log off. Have a wonderful evening, and I'll see you all next week. Missed that. So why some telescopes are located in space is to depend on what we want to observe. So for example, if we want to observe X-rays, our telescopes on the ground needs to be at places that's as dry as possible and as high as possible to get away from water vapor in the atmosphere to detect X-rays. And one other thing is our telescope, our atmosphere is also very unstable. So one thing is about that is for example, to detect high energy particles or high energy electromagnetic rays such as X-rays. Those are absorbed by water vapor in the atmosphere. So to get past that constraint is we need to build telescopes in places that are as dry and high as possible to get away from the water vapor. And our atmosphere is also unstable. So to solve those problems, we can put some telescopes in orbit around Earth. Then you don't have any interference from the atmosphere, and you can also detect the electromagnetic rays what you want. So therefore, it all depends on what you want to observe. So therefore, some telescopes are in space and some is in orbit. I hope that answers your question. Awesome. I'm also going to log off now, so have a wonderful evening and see you all next week.